Hello, everyone. I'm RAFAL, and I'm speaking to you from Krakow, from Poland. And my talk is titled Mutation Testing with Pete. But first, a few words about myself. So I'm an integration team lead at Hazelcast. Before I worked at Google and CERN. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking and trainings, but on a daily basis, I'm a developer. A few words about my company, Hazelcast. So we are a distributed company. We are an open source company. And we are distributed in two meanings. First meaning is we produce distributed software. Our software is Hazelcast, which is an in-memory data grid used by many people for caching. Our second product is Hazelcast Jet, which is a library for stream processing. And our third product is Hazelcast Cloud, which is basically Hazelcast put as a service. But we are also distributed in a second meaning. And the second meaning is that we all work remotely. We are around 40, 50 engineers, and we all work from all over the world, and we always work this way. And today I will tell you about mutation testing and also how we use it in Hazelcast. But first, a question. So, do you know why NASA spacecraft burned in the atmosphere of Mars in 1999? And do you know that it was related to the fact that mutation testing was discovered in 1971, but it was not really used until 2012? And so I will answer these questions during my talk. But first, you can imagine two engineers discussing. So this situation could have happened in NASA. I wrote code for the spacecraft. How do you know that it works? I just know, or I feel it. So, that is what happened actually in NASA. The code was not tested. Someone assumed it worked, but it didn't. And in December 1998, the NASA launcher went up to the Climate Orbiter spacecraft into space. And it went up. It wanted to reach the surface of Mars. And when it was half of the year flight from Earth, then the signal was lost, and we couldn't contact with this orbiter. And what happened? So there was a bug in the code. So the ground computer calculated everything in non-metric system. They used pounds. However, like the orbiter used the metric system, and there was no conversion in between. So the speed of the orbiter was too fast, and the orbiter passed too quickly through the atmosphere of Mars and burned. So there were no people on board, so at least nothing. I mean, you can say that, shit happens, nothing really bad happened. But you know what, like this orbiter, these NASA devices, they are super expensive. So this orbiter alone costed more than $300 million. So if you take this amount of money, it would be like 234 Americans working all their lives to earn the money for the orbiter. If you calculate this on the Polish people, it's even worse. It's like 700 people working all their lives just to earn money for this device. So, and it's all because of two engineers discussing. So how this conversation should look like when they discuss. So the first guy is saying, like, I wrote code for the spacecraft. How do you know that it works? I wrote unit tests. How do you know that your tests work? But really? So you write code, and then you write test to test your code, and then what? You write test to test your test, and test to test the test of your test, and test to test the test of your test. It doesn't make sense. So does testing make any sense at all if we cannot prove that our tests are right? And actually, there is a way to test your test without writing more tests. Imagine the following code. The simplest code possible, just calculation of two numbers. So we calculate we add two integers, nothing more. So we write a unit test to this, and how we check that the unit test works? We usually write code coverage. So we say, okay, if this was covered, this is green, our tests are good. However, like if you think about code coverage, according to if you just think about it, use common sense, or you can even what does code coverage really do? And if you read like books from Uncle Bob, like you may find this quote that code coverage does not prove that you have tested every line. All it proves is that you have executed every line, and that is a big difference. So we can have this code, and it's going to be perfectly covered. This A plus B can be perfectly covered with a test like this. So just no assertion, nothing. Just execute this code. Coverage is green, 100% coverage. So you see, we need something better. We need something better than code coverage to give the information if our code was tested. And this something better was actually discovered a long time ago. It was discovered in 1971 by Richard Lipton. So Richard Lipton was a scientist, and he asked a more fundamental question. He asked why do we test? Why do we test at all? How would NASA be better if they had test in 1908? And the conclusion was that we write tests to detect bugs. So think about it for a moment. If there is no bug in your code, you don't need to write tests. There is no reason to test anything. So your test is good if and only if it catches a bug. So we can reverse this strategy and introduce artificial bugs and check if our test fails. Because if we introduce a lot of artificial bugs, our tests should fail. Then they are good in detecting bugs. That is exactly what Richard Lipton described in his paper. So he said, if you want to know if a test suite has properly checked some code, introduce a bug. Now, how can we do it in practice? Let's go back to our example. So simplest example, we have a code, simple sum, A plus B. How can we introduce a bug into this code? So we can change plus to minus. That is clearly a bug. We want to have a sum, but we have a subtraction. So this code with the bug is called a mutation of our production source code. And now if we run our test suite against this code, if our test suite fails, it means, okay, we cover this code. However, if it doesn't fail, even if we change plus to minus and this doesn't fail, we didn't write the test in the right way. So that introducing a bug is called mutation testing. So we may ask, is it the whole idea behind the mutation testing? And actually, yes, that's it. We create artificial bug, we check our tests against it. So the idea is pretty simple, but before we go further, let's see the terminology we will use. So this artificial bug is called a mutation operation. Code with artificial bug is called a mutant. Now, when our test suite fails on the mutant, it's called that we killed the mutant. However, if our test suite succeeds on a mutant, it means that the mutant survived. So if we have our example, A minus B. If our test fails, we kill the mutant. If it survives, so in this terminology, killing is good. If we kill all the mutants, our tests are perfect. Okay, but even say but my code is much more complex than adding two numbers. Adding two numbers is simple. I know when my tests are fine. That is why we have a lot of mutation operations. So, and we even, there are so many of them that we make categories of them. So the first mutation operation, what we do is like some math operation. So we change plus to minus, minus to plus, multiplication to division, etc. So we change the math operations. Second category is we change the boundaries. So we have our if condition. So instead of less than, we put less or equals than. So it's changed. So it's an artificial bug introduced in our code. Then we can negate some conditions. And then there are some complex operations, some removing if operations, for example, or removing some method calls, or modify return, or modify some constant. There are some more actually. So now how it works. So we have a lot of mutation operations. So how we use them. So we have our code base. So this is our code base. And now from this code base, we apply mutation operation in one place only. So we create a second binary. This is our mutant. This is mutated code. And now we provide a lot of mutation operation, create a lot of mutants. So we have a lot of binaries with our code. And against each of this binary, we run our test suite. And now if for each mutant, for each mutated code, at least one test fails, it's good. The mutant was killed. So if we kill all the mutants, that means that our tests are good. We covered all the scenarios. However, if there's at least one mutation on which none of the tests failed, we have a problem. That means that this part of the code is not well covered by our tests. And this, we should investigate it and write better tests. So next thing probably you think about is, do I need to change this code on my own? Like it sounds crazy, like to change all the code on my own. And luckily, no. There is there are different frameworks, but for Java, the most used one is PIT Mutation Testing framework, which does all this mutation and testing for you. And you can use this PIT mutation either from the console as a tool, or you can install this into your Intellij or Eclipse, or you can use it with Maven. I will show you some scenarios like that. I personally always use it from Intellij because it always check my code. I wrote test, run an Intellij. I see the code which was not covered. The same way as you usually run the code coverage. So this is like code coverage, but better. So if we, coming back to our code, so this is our super simple code, which has 100% test coverage. So we can check how it looks like if we apply our PIT framework to this. So let's do a quick demo and show how to use it first. First, I will show you how to use it from Intellij on this simple code. So if you open an Intellij, I have exactly the same code with the calculator and with the simple operation and calculator test. So this is all very simple and provides 100% coverage. You can even run this test to see that it really works. You can also run it with test coverage to see that it really covers where our code. You see this 100%. It's all well covered, even though it's not testing anything. So that means we need something better. So what we can do right now is to use the PIT. You can install a plugin to Intellij, and then if you edit configurations, you can specify a new configuration and select the pit runner. So if we look at the pit runner, we can give it a name, some pit test, and then have some parameters. Just maybe not. Yeah, you can have a look at these parameters, basically saying where to take the test from. And if we accept it, we can run this mutation test suite. So let's start it. It should be fast because our code base is very simple. It created 2 mutants, and you can already see that there was a generated mutant, but that it was not killed, which is bad. So that is the end of the first demo. So you see, like what we've seen is like we created the math mutator. It changed this plus to minus, and that the mutant was not killed. So it's bad. So no coverage means that there was no test addressed here. Timeout means that the test timeout, because you mutate random things in your code, so it can result in a different scenarios. For example, there can be timeout because we created an infinite loop. That can be non-viable, meaning that some JVM bytecode is invalid, or we can have some memory error because because of the random change in the code, we can exceed the memory, and so on and so on. That is why you have, it's not only killed or survived, but there can be some other scenarios. If we would like to improve our test suite, obviously we can write a simple test, adding 2 numbers, checking the results. And then we should see in the console, our mutant was killed, so we are happy and our test is good. But come on, do I really need to read the console? It's like 21st century. Do I really run all this test and check for the console? And luckily, no. Pit framework generates a report for us, and is fixed. So this is actually a positive scenario. So how it should look like. So we can run this test suite again. And if you run the same, we should see that the mutant was killed. You can see it in the console. But what I actually really want to show you is that we can also, that the report was generated, and we can open this report in the browser. And then the whole code base, your code base is displayed here. And we can check every class, every class, what is the code coverage according to the mutation testing. So this way, it's still called code coverage. However, it's better code coverage because it can also give you some information like what mutants were created and if they were killed or not. So it's pretty straightforward. So I really recommend you using this. If you write some code, just click one button in Intellij and check your code coverage in a better way. But when I show these examples and etc., so everybody tells me to say, okay, it sounds great for a small project because you can create this mutated code. It's all fast and all good. However, like my project is way bigger than that. So what to do with bigger projects? Will it still work the same? And that was actually also my first concern when I've heard about mutation testing. Before the idea is great, but there are so many possible mutations, and we change the random places in the code. So will it cover like a big code base? So what we did in Hazelcast, we tried it on one of our plugins. This is not super big plugin, but also already some code base. It's like it's a little more than 5,000 line of code. It has 12 classes, so it's still a relatively small code base, but it's something good to try on. And it's it's open source, so it's easy to test anything on it. So let me show you how we do it in Hazelcast, how we use the speed framework, and what are the results with the short demo. So this time I will show you how to run it in console and also what we do with this. So the first thing, if you open our project Hazelcast Kubernetes, you'll see we added this one profile for the PIT. So this is all actually you don't need to add anything more than that to your project to run your PIT mutation testing with Maven. So we specify the plugin, and that's basically it. So if I can show you, I can clone this this project. So if we go to the code, git clone, I can show you how to run this. So let's open this project, and then if you run this command, like profile test and then mutation coverage, this will generate the whole HTML report for you. So it's pretty nice, and that's it. That's all you need to do to run the mutation testing. I think it does make sense to wait now, because I tried it before and it took like 25 minutes. So we don't have so much time. So I'll show you how we do it. We actually integrated this with our CI, and in our GitHub Actions CI, we generate always after every push to master, we generate a code coverage report. So you can see we run exactly the same command with mutation coverage, and then we use another GitHub action to publish this report on GitHub pages. GitHub pages actually are very good for this, because it's like a static hosting for your website. So so after you run this action, so you run this action, and then the PIT coverage is run, and the report is generated I will show you in a second. So this is this PIT coverage. On GitHub Actions are fast. It took 2.5 minutes, but on my local it took, I think, 25 minutes or something like this. So yes, and you can see the same report on our published GitHub pages. So we publish on the GitHub page, and you see the whole report of the whole code, how it's covered according to the mutation testing. And it's interesting to check your own code, to see what you didn't cover right. So we can see, for example, that there are some lines not well covered. For example, this should be covered, or okay, if we change this line to null, it's still the same. So this is definitely not well covered. We probably could discover where more places like this. It's just, it may, it's maybe better to show not on your own code base, but you get the idea. So what I recommend doing is putting your, if you have any project, put the PIT testing code coverage generator into your CI pipeline, and then you can always check, what is the state of your code. Is it well covered? Coming back to our presentation, so this is all thing, this mutation testing. So why NASA engineers didn't use it in 1998, even though it was discovered in 1971? So if we look at the timeline, so Richard Lipton discovered this, wrote this paper in 1971. But only in 2000 there was a first Java framework called Jester that provided this functionality of mutation testing. And in 2012, only then we have this PIT mutation testing, which is really widely used. So why is it like we have like what 40 years almost gap between like a good framework and the discovery? So why is it so? And actually there were two reasons why mutation testing was not well adapted. First reason is there is something called equivalent mutants. So to explain it to you, let's look at the following code. So this is a valid code, and you could see a code like this. The problem of this code is that if we mutate the code randomly, and for example remove this line, semantically nothing has changed. So you see like that we have a mutant which is equivalent to our production code. That is why we may, even though all your test suite passes, that doesn't mean that it's a bug. So this is a problem called equivalent mutants, and it's actually quite hard to solve. The PIT mutation testing doesn't really solve the problem of equivalent mutants, but it made the mutation that are highly probable to end up with the equivalent mutant disabled by default. But you can still enable them. But it took all these operators and say, okay, with this operator, it's highly probable that we will end up with equivalent mutant. So let's do not enable them by default. So, but it's still technically it's still possible with PIT mutation framework to have equivalent mutant and to have like false positive, false negative. And the second reason what was the problem with mutation testing? What was the performance? You might have already suspected this. We create we create a lot of mutated code, a lot of mutants, and we create and we have a lot of test suites. So, and we need to check each combination. So even on this diagram, if you look at this diagram and the combination between tests and mutants, there are almost 1,000 combinations on this small diagram, but your code base is way bigger. So the idea that PIT framework introduced was simply that you first run the standard code coverage on your code and then check which of the tests are related to this code coverage. And then only this code is checked, only the mutant from this code are checked by this test. So then you don't have all the combinations. So it's way better. And obviously you can run all these things in parallel. So it's also some optimization. What PIT framework also does, another thing, is test prioritization. So it run the most probable to kill the mutant around first. So they do a bunch of smart things, so that in result that the execution time is not so bad. That is why you are able to run it really in your own environment. And everyone is happy. I mean, it's a very good solution, actually, this mutation testing. That's why we adapted this in Hazelcast. Now, you can already, maybe I convinced you to use it, but you may say okay, that RAFAL, it's great. I will run it locally before I push it to the repository, but what about my team? And let me tell you a story here. So not so long time ago, I worked in the banking industry, and we had 3 locations. One was in Stanford in the US, second one was in Krakow in Poland, and the third one was in Hyderabad in India. And each team developed the separate modules of the same system, so we didn't cooperate very much. But since it was the banking industry, there was a strong push on having tests and avoiding any bugs. So the bar for code coverage was very high. We had actually 100% code coverage in our CI pipeline. So So if anything was below 100% code covered, there was a build failure and you couldn't merge the code. And everything was fine. I was writing code. I was all happy until the moment when I had to write a completely new module. And then the construction of the module was that there was always like a main module class when the module started. So I created all the classes, wrote the test, but then I thought, how to test the main class? I mean, to run the main class, usually you would need to run the whole system. It was actually not possible in this case of this system. So I ran to something I called a main class paradox, that you can test everything, but the main class is usually something you cannot test in your unit testing. You'd need to run some acceptance testing, etc. But I had to do it because, like, if the code coverage, my code coverage was lower than 100%, I couldn't merge the code. So I thought, like, let's see what other people do in their modules. So I checked actually the code base of the Hyderabad team. I checked what they are doing. I read all the code and tests, and I found the test for the main class, and I found like that the test had given when, but no assertion. So it was exactly the case. Like, so I don't know. It's I don't know what to do with people who write tests without assertions. Should we laugh on them or should we get angry? That is why, like, the moral of the story is that 100% coverage is not a good idea to have. Enforcing this on your team, it's usually not a good idea. And how to address it? I think better way to address it is to do what we did in Hazelcast and put like not like the coverage bar, but to generate the report, to always have access to the HTML report, put it into your CI, like Jenkins or Travis or GitHub Actions or whatever is your CI, and publish somewhere the report. Then you should every week or every other week check the report. Okay, what is my code coverage according to the mutation testing, and then act on that, and not necessarily forced to some basic numbers which doesn't make sense, like the percentage of the numbers. So if I convinced you to using this, integrating it into your CI, so you may also you may already use it. If I didn't convince you, then the last question actually is like, do people really use it? And nowadays there are many companies. I know from the historical point of view, the CERN was one of the first to introduce the mutation testing. It was also used in the Norway polling system. So it's actually, and now I see more and more companies that they just integrate it and use it. So my recommendation is to test your tests and think about the freedom it gives to you, about that you can then trust your test and really have good results, improve the quality of your code. So test your test, because otherwise something bad can happen, or you can lose a lot of money, or you can feel shame across other teams, or people can laugh on you or be angry. Thank you for listening to this talk.
Thank you, RAFAL. We can wait a bit for questions.
Sure. I'd be happy to answer any questions.
You talked about performance, but how much down do you see from introduction of unit test in practical sense? Like, what's your experience with how much slower the build becomes because you put mutation testing on it on the project?
Yeah, you can run it actually in parallel, like a separate, for example, a separate. We do it like as a separate GitHub action, so it's like in parallel to normal build. In our case, what I showed, like on what I presented with the GitHub action for one of our modules, it was like I think this mutation testing phase took like 2.5 minutes, and like in total it took I think 5 minutes to generate the report and all this thing. But it was very, quite small module. But as I told you, even if you have a big module, it can be long, but it can be run in parallel with your standard build.
What you're saying, I guess it depends. If you have already, let's say your build is taking 1 hour, your tests, and now you put, of course, you're paying for a certain number of machines, and of course, I mean, all of that is already kind of at the limit. It's already running at 100%.
Yes.
So maybe you have to maybe pay twice more to run, or 3 times, or of course, depending. Does it scale linearly with the code, or more like exponentially, or like quadratically?
Yeah, it will more or less. I mean, it should be exponentially, but thanks to this things like that the PIT framework first run the normal coverage and only then uses part of I would say it limits the tests suite against your mutants to minimum, so it will be more or less linear. You will see with your code base and tests.
That's great news. Well, I don't see any questions, so thanks again for your presentation.
Thank you for having me. Yeah, it was great to be here, at least virtual.